Hello, and now we will be discussing Chapter 3. We'll go through sections 3.1 and 3.2, and then we'll go through the other sections a little later on in different recordings. So one of the things that we have to learn to discuss in physics is vectors. And we're going to be looking at something called a position vector, and this vector is going to be labeled R, and it's going to have an arrow on top. And the position vector of an object in a plane is going to be the displacement vector from the origin to that object. Its components are going to be given in X and Y. The average velocity of the object during a time interval is going to be its displacement. So the change in R is going to be considered the displacement. The change in the displacement vector divided by T is going to represent the average velocity. So the change in the displacement divided by the change in time. The change in time is going to be considered a scalar quantity, and so the direction of the average velocity is determined entirely by the direction of the vector displacement change in R, delta R. The average acceleration is basically going to be your change in velocity with respect to time. If you take the limit of either one of those quantities as delta t goes to 0, then you're going to be looking at the instantaneous velocity and the instantaneous acceleration, respectively. So if you look at it graphically, the instantaneous velocity is going to be the tangent to the position versus time curve. So you've got your position here, you've got a position here, and you can see the average velocity as you go from point A or point 1 to point 2. You can see the change in X, change in Y. This is going to be the change in R. And the instantaneous velocity vector is always going to be tangent to the path that it takes. So this is always going to be tangent to that. Now, the vector R, your displacement vector, if we look at it component-wise, in other words, take the absolute value of that vector, it's going to be the square of the individual components. That's going to give us the distance. That's an important detail to remember. This is material that we've already discussed here, where you've got the position of the ball at any particular time. It's along the resultant vector. The tangent vector to that is going to be your velocity vector. Again, we've discussed the average velocity here. One other important thing to note is that if the object is moving only along the x-axis, then the y component is going to be 0. And likewise, if it moves only along the y-axis, then the x component is going to be 0. And we've got our discussion of instantaneous velocity here. At every point along the path, the instantaneous velocity is tangent to the path, and speed is going to be the magnitude of that instantaneous velocity. If we look at our graph here, you can kind of see the angle that's being made between Vx, Vy, and the velocity vector V. Obviously, the velocity is not moving all in this direction or all in that direction, but a combination of the two. And if you look at the displacement and you're looking at the change in the individual coordinates, V of x is basically, if you're looking at the instantaneous velocity in the V, or for V in the x direction, you're looking at the limit as the delta t goes to 0 of delta x over delta t. Same thing goes for the y direction. And the length of the velocity vector is pretty much going to be the same thing as what we saw with the resultant vector. It's just here we're dealing with velocities as opposed to the distance. If we're looking for the angle that the vector makes, then we're going to take the inverse tangent of Vy over Vx. You can kind of get that from the trigonometric relationship here. If you slide that vector over here And then you can see that the tangent of this is going to be the opposite over the adjacent. You just take the inverse of each side in order to be able to get the value you're looking for. So there are plenty of examples down here to work. Go through those, and then we'll move on to section 3.3.